So for any xy in the Hilbert space, we take the finite one, the rank one operator txy, and we define the linear functional chi on the txy. That will give you a bounded sesquilinear form on x cross y. Okay, so B is from H cross H to C is a bounded sesquilinear form. Okay. So there exists an operator. There exists an operator T in B of H such that B of xy equal to Txy. Okay. This is follows from, I mean, if you fix the x and vary the y, you will get a linear functional. And every linear functional corresponds to a vector. And that call that vector as Tx. Okay, this is an exercise you can see. And that vector corresponds to Tx. Okay, and x going to Tx will give that operator, and T is bounded precisely with that norm, whatever that be. Okay. Okay, and this also proves, so this is the bounded linear functional. Okay, and this also proves that, so there exists a T here. Okay, this is T. Txy. Okay. So dxy equal to txy. Okay. So now this is also equal to chi of txy, right? Chi of txy equal to this. But notice trace of txy, t. What is that? That is equal to trace of in the trace, but there is no square root. It's not a problem. So trace of txy is equal to trace of, so you can take an orthonormal basis with take En orthonormal basis with E1 equal to, let me see what we need. This is equal to trace of txy summation n equal to 1 to infinity En orthonormal basis. Okay, txy, sorry, txy, doesn't matter which way you take. Okay, txy, or you can take the other way. En, that's what you want to do. So that is equal to summation n equal to 1 to infinity. So you get the T star En other side. Okay, txy En. Okay, now that is equal to summation n equal to 1 to infinity. Txy En is En y En, right? En y x, sorry, x T star En. Now take an orthonormal basis. Take orthonormally Vn equal to y. Okay, and all the other elements in the orthonormal basis are orthogonal to y. So this will only y will survive, right? So this will imply that only y will survive, right? So this is equal to I want to get txy. Sorry. Ten.
You've got it. It's.
Huh?
I think you got that product x comma t star y.
This no. Where is
You've
it?
got.
You get.
You took E1 to be y.
Oh, En is y. So very good. Sorry. Yeah, sure. It has to be. It will survey only for that. This is equal to x T star y for sure. Very good, sir. Yeah. I'm just looking for where is y will go away, what will happen. That's what I want to do. So that is equal to, yeah, this is equal to txy. Good. Thank you. Thank you. This is a hangover from that confusion. I'm sorry. So what we have got that trace txy t equal to this. Okay. So this implies, what does it imply? That is what we have defined it as. So this implies chi of txy, which is what we have defined to be equal to trace of txy t. So this is true for all rank 1 operators. So hence this implies chi of txy, sorry, chi of any s is equal to trace of st for all finite rank operators, right? Finite rank operators are linear combination of rank 1 operators, right? For any finite rank operators. F in f of h. Okay. So this and notice that, I mean, we have already proved. So what do you have? We have the about sesquilinear form and other thing we have proved. And from that, it will follow that the norm of t is less than or equal to norm of chi. Okay. It will follow here. There exists a t with something like this, and norm t is less than or equal to norm chi. I mean, that's the property of the definition using that bilinear form. So because of this implies, I mean, chi t is actually a bounded linear operator, bounded linear functional. Chi equal to chi t on this. Okay, this implies chi equal to chi t on pH. We are actually proving that this no, chi is less than, yeah, norm t, no? Did I use norm? Yeah, norm t. We are actually proving that norm t is also less than or equal to chi, norm chi with. So this implies with norm chi equal to norm chi t. The other direction is already proved. We have proved it actually. We have proved the proposition. I'm sorry about the confusion, but we can go through it again later. I mean, if you go through it, and if you have a problem, we can go through it again. I can tell you, I can explain everything. Okay. Okay. So this is the proof. So this proves that the dual of trace class operators is all operators. I have given everything in the proof. Okay. Okay. Now I want to give an assignment, but I will more or less give everything, every detail here, and you just have to. I mean, like this finite rank operator, you have to do some ugly calculation. What I have done. Okay. What I am trying to do. So this is about integral operator. Before that, I want to prove the following proposition. So H is a Hilbert space. Then let En be an orthonormal basis for the Hilbert space for H. Then T, En, which are finite rank operators. T, En is an orthonormal basis. You take, sorry, En, Em. You have to take En, T, En, Em. Okay. N and M, N in N, N and M in N is an orthonormal basis for the Hilbert-Smith operators. Okay. Proof. I mean, yeah, this is what I want to give it as an assignment. Even if I give the whole proof, you please write it, okay? Because that's a good exercise for you. So that's what I want you to do. So since you can directly hand it over to me the week after the exam, okay, I can come there, okay? And the earlier assignment. This is assignment. So E and B an orthonormal basis, then T, En, which are all finite rank operators. Okay, this is contained in finite rank operators. Okay, is an orthonormal basis for Hilbert-Smith operators. What do you have to prove? So we have to verify that TEN EM. Okay, you verify TEN prime, or you can call it as TNM. Okay, that is easier. But anyway, since we have used the notation, I'm using it here. TEM prime. Okay, if you take this, use, I mean, there will be a lot of products and trace computation which we have done, which we will go through it again in the next class, discussion class. So this will be exactly equal to delta of n prime, delta of m prime. Okay, so this will prove that this is a orthonormal set. Okay, and you have to prove the orthonormal basis of it. So how do we prove orthonormal basis? For that, if you take any t in B of h, any t in B2 of h, okay, so then you want to find the inner product of t with t en en. Okay, and if it is 0 with respect with all n and m, t should be 0. That's what we want to prove. So if you compute this inner product, which is just trace of t en em, I take it, I mean, maybe t star or something. You take t star or something. Okay, or you take this way, t star. So that is equal to t times this, and you will find, you do the calculation what I have already done, and that will precisely equal to t of en, possibly n and m interchange. I think this is correct. Okay, it will be t en em. So if this inner product t star with t en em is 0, then t en em is also 0. Okay, so that will imply that this is actually orthonormal basis. Okay, that will prove that it's an orthonormal basis. So this is an assignment. Okay, so I hope this is okay. So the final thing we want to do in the next 8 minutes, integral operators. Maybe, okay, this is not needed. I might have defined this operator earlier. I don't know whether I defined. It's okay. So let's consider H is L2x mu with respect to some measure mu, which is a nice measure called radon measure or something. I mean, if you use the property. Because we want to use the Stone-Weierstrass theorem. Stone-Weierstrass theorem implies that the functions of the form, see, f tensor g, you define f tensor g at s equal to f of s g of s. Okay, it is just the sorry, it's a two variable function. Sorry, at s and t equal to f of s g of t. Okay, so this is a function in L2 of x cross x. Okay, x cross x, mu cross mu. This is a product measure. Okay, now this function f, this span of this span, closure of f and g in L2x is dense in L2 x2 with mu tensor 2. Okay, again it will end in 10 minutes, so I will do it before that. So the reason for this is Stone-Weierstrass theorem will imply that C of x product, C of x, C of y kind of thing. You take the product of those things, f tensor g, this kind of f tensor g, f tensor g. Okay, I will discuss this later. This is just one thing. I mean, if it ends up in the middle, it will be a problem. So I will just explain this integral operator in the next class, and we will discuss more in the next class. So I haven't defined what is integral operator. I will define all these things in the next class, and then so next class, I mean, I will confirm it in the night today. So we will have it in CMI. Okay, I'll come there, and it will also be through Zoom. I mean, I will have the computer on, and you can watch it. I will do it in the board. Okay, so I will send it a mail through Moodle today. Okay.
Sir, will it be possible to start the class at 3:30?
3:30 tomorrow? Okay, I
Yeah,
thought you
okay.
have some class and other things, so that's why you fixed it at 4:30. No, 1 second, I will stop this recording.